All right, so extreme values of a function. So first of all, there is, yes, another theorem. I know, it seems crazy, right? So this one we're not going to write on a piece of paper. Really, this is like an idea, okay, kind of theorem. This is saying, the extreme value theorem is saying if you have a continuous function on some sort of closed interval. So here are some closed intervals. So these are my examples, okay? So if you have a continuous function on a closed interval, so there's an f, a g, and an h, then what has to be true, then there has to be both an absolute maximum, the very, very, very highest y value, because that's the maximum of the function, and an absolute minimum in that interval. So, for example, the absolute maximum, the absolute minimum of f would be maximum is here, minimum is here, okay? The absolute max and min of this closed function that's continuous, the absolute maximum looks like it's right here, right? That looks higher than this endpoint, so it's right here. And then the absolute minimum is obviously right here, okay? So that would be the y value of the maximum, or the y value of the function is the absolute max, and the y value is the absolute min. Because when they say the absolute maximum, they're saying the absolute maximum of the function. What is f? F is, you know, a y value, okay? And then something like this as well. So you have a closed continuous function, you have an absolute max, you have an absolute min, okay? So that is extreme value theorem. That's all it is. Okay. And then there's some words that you have to know. So it's extreme values are called absolute. They're also called global. So sometimes you'll see global maximum. That's the highest y value in the given interval, like we talked about the y value. And absolute min is the lowest y value. It's also called a global minimum. So globe makes sense, right? It's everything. So absolute and global are the same thing. Okay, but there's two other terms that are really popular and really important. So we talked about this a lot in pre-calculus last year. So there's also a local maximum and a local minimum. These are called relative maximums and relative minimums. The reason why these are relative maxes and relative mins is because a local max or a local min has to have some sort of slope change from positive to negative, like it goes up and back down. So it's the top of a hill for a local max. It's the top of any hill. Or it is the bottom of a valley. So the slope is going from negative to positive. So for example, this has an absolute max and an absolute min. It has no locals. This has an absolute max and an absolute min. It also has a local max at the same place as the absolute max. It also has a local min at the same place as the absolute min. This one has an absolute max and an absolute min. This one has a local max, but there's no local min because the local min has to go down and then back up. This is the only one that goes down and back up, but then both of these go up and down, up and down. So these are local maxes. This one is the only local min. All right, so that's the difference. Okay, so then you have this somewhat crazy looking function, and I want you to classify all the extreme values. So what would be A? What can you call that, if anything? And I want you to try. I don't want you to just copy me. Okay, I want you to try. Give it a couple seconds, pause, and then let's check your answers. And hopefully these are your answers. So A is an absolute min. It's the very, very lowest on the whole closed function, right? It's closed because there's an endpoint and an endpoint. So A is the very lowest. That's an absolute min. There can be only one absolute min unless A and E, like E was down here. Then they could both be absolute mins because they're both the same y value. Okay, so A is our absolute min. B is our absolute max, and it's a local max. C is just a local min. D is the top of a hill, so local max. E, bottom of a valley, so that's a local min. And then F is nothing because B is higher, so it's not an absolute max. And it's not a local max because it doesn't go up and then back down. Okay, what is the absolute max value itself? The absolute maximum value is where the highest y value is, and the highest y value is 7 at point B. Okay, what about the minimum, absolute minimum value? So the absolute minimum y value is y equals 0. So 0 is the minimum y value, the minimum value, technically. Okay? Okay. So then it gets into, again, you guys remember velocity, acceleration, all that stuff? Okay. So this is very similar, but, written a little differently, okay? So first of all, there's these things called critical points. So a critical point is where your derivative, your first derivative equals 0. So it would be like when we find the velocity and set it equal to 0, that's a critical point. So what we're doing now is we're not just using particles, we're actually drawing a graph. So using some function, we want to be able to draw that graph, okay? So we know how to graph, plug in x, plug in y. There's a different way to do it, okay? So we set that equal to 0, those are our critical points. Or it's undefined. So critical points are going to be where f prime is either 0 or undefined. Okay, so you guys already know this. If the slope is positive, right, it means f is increasing. If the slope is negative, it means f is decreasing. You know this already. This is stuff we know. Okay, a relative max and a relative min. A relative max is when slope changes from positive to negative. So you're going up a hill and down a hill. So slope is positive, slope is negative. Relative min is from negative to positive. Okay? And then critical points. F prime can stay positive or f prime can stay negative as long as, like, let's say you have a 0. So let's pretend, I'm going to draw this for you. Let's pretend you, remember your velocity? And then you start at 0 and you go to the right, and let's say this is a 2. Let's just pretend. Let's say on the left side is a negative, on the right side is a positive. So this means that the function, or the particle, so if we're talking about particles, this means that the particle is going to the left until 2, and then it's going to the right. If we're not talking about particles, if we're just talking about the function, and we change this instead of v into an f prime, then that means that our f graph is going down and then it's going up, okay? But it is possible for this to happen, right? That's possible. We could plug it into our original function and get positive and positive, but then we still get the 2 here. So an example of this kind of f prime function is when you have maybe x minus 2 quantity squared. So if this was true, if you plug it into the left side, you get a positive. If you plug it into the right side of 2, you still get a positive. So this means you have a positive slope and then a 0 slope and then a positive slope. I want you to think about what that means. If you have a positive slope and then a 0 slope and then a positive slope, it's going to look something like that. See how it's positive and then 0, it zeroes out, and then it's still positive. So it's going to look something like that, okay? So that's going to be your original f graph. So that's going to be your original f graph. It has to look something like that based on my slopes from f prime. Okay, so we're going to get more into that part in a second. Okay, and then is there anything else down here? Kind of. Okay, so that's kind of what I just did. So let's say you have an f prime. You have an f prime little chart. You have a sign chart, right? So let's say you draw it and then you get a positive, a negative, a positive, and a positive. So what you would do is you would, so right here I would have like kind of dotted, right? Because that's where like things change. So positive, negative, positive, positive. And then these are 0 slopes. And then I would smooth it out. So maybe it looks something like that. And that's what I drew here. So you can see I went up, down, up, up, because that's what the slopes told me to do. So my slopes, f prime of f, are positive, negative, positive, positive. but then I should have 0 slopes at those 3 places at -3, 0, and 1. So up, down, up, and then I smooth it out. So I have a 0 slope, a 0 slope, a 0 slope, but then see how my curve still follows my up, down, up. I can't like, you know, make it go some other direction. No, it has to follow what I already did. So it just smooths it out. Okay, so these new ideas over on the right side. Okay, now we're talking about, instead of acceleration, we're talking about on a graph, they're called inflection. We're getting inflection points when we solve for f double prime. So the second derivative, we usually say for particles is acceleration. But for us, if we're drawing a function, that is helping us get our inflection points, and that's where your f prime changes to positive, negative, or vice versa, or you know, whatever it is. So you get that second derivative, and here's what it means. So second derivative is positive, means that your original is concave up. What does concave up look like? Concave up from here to here would look like that. Concave up, right? The bowl is like facing up. Or from here to here, if you're decreasing, concave up. Those are both concave up, all right? And then if you have your f double prime is less than 0, if you're negative for your second derivative, that means that you're concave down. So if you're increasing and concave down, that would look like this. See, you're concave down. And then maybe you're decreasing and concave down. You would look like this. Still concave down, but now you're decreasing. So you can be increasing or decreasing, and then you can be concave up or concave down, depending. So those are both concave up, but this is increasing, that one's decreasing. These are both concave down, this is increasing, this is decreasing. So that's still positive. I mean, it's still possible. Okay. So inflection points are when your f prime is changing from positive to negative or negative to positive. All right. So if I draw, a critical point. So this is still a critical point technically if it stays positive and positive. So if you solve for 0, if you get this equals 0 and you solve for it, so it's still a critical point, but it might not be an inflection point, okay? Critical just means important. So it's still an important place and something weird happens, okay? Okay, so let's say you have something like this. I'm gonna draw it for you and then I'll show you like a nicer version. So this is your second derivative. For your second derivative, your concave, does it have second? Oh, well, it doesn't have the first derivative. That would be really helpful if it had the first derivative. But this should be concave up and then concave down. So if I think about it, concave up, so let's say it's increasing. I don't know if it is, but if it's increasing, I can be concave up and then I can be concave down. And then this says something weird, so I don't know what's happening. And then there's maybe a hole. I'm just pretending. And then I'm still concave down. And then I'm concave up. So that is one example of what it could look like here for f. That's one example of what f could look like. Here is, here's the same example. I guess I always use that, okay? So if you want to see another example, so instead of increasing and then decreasing, maybe we're starting with decreasing, but it's concave up. And then it's concave down. And then something super weird happens, and then we're concave down still, and then we're concave up. So see how like that's possible too. Concave up, concave down, concave down, concave up. So that's still possible, and we're still negative to negative. See, negative to negative, and something weird happens to that second derivative. Oh, it's a weird cusp thing. Yeah, it does look weird. Okay? All right. So here's what I want you to do. On your paper right here, I want you to, at every point, tell me, is f prime positive, negative, 0, or possibly undefined? So I'll do the first one with you. Here, I can see the slope of f. This is the original function f. The slope is negative. So I would say f prime is negative. I draw a little minus, okay? And then f double prime, what's f double prime? Oh, that's concavity. Does that look right here at A? Is that concave up or down? Well, that's like a, if you extend it, it would be like a bowl going up. So it's concave up, okay? So I would have a negative for slope, and I would have a positive for concavity. What about here? I'll do one more with you. Right here, what is your slope at B? It looks like it's 0, so I would put 0. What is your slope, or what is your concavity at B? Well, obviously it's a bowl going up, so it's concave up, okay? Can you do the same for point C and D and E and F and G? You do it in pencil, don't just copy me, guys. Don't copy me. Okay, I'm going to show you the answers. Okay, so let's say like this. Let's say this is true, okay? So we talked about these two. I'm going to say this has a this positive slope, and then your second derivative is either 0 or undefined. We don't really know if it's 0 undefined. And then here you have a slope of 0, and then it's definitely concave down. And then right here, it's changing from concave down to concave up. So you can see right here, it's 0 undefined for f double prime. But for f prime, our slope is negative at E, so that's why it's negative. Here you have a slope of 0, and then obviously concave up. And then here you have a positive slope, and obviously still concave up. Okay? What are your critical points? So you look back, and what are your critical points? Critical points are where you have your first derivative equal 0 or undefined. So you list them. So it happens here and here, because these are critical, and here and here and F. Oh, why did I say it was F? Oh, F is here. Sorry. So F is here. Okay. So, and then I also listed, what is B? B is a local min, and we can call it an absolute min. So do you agree? I hope you do. C is just an inflection. C is an inflection point. So that's where you're changing from concave up to concave down. So that is an inflection point. D is a local max. E is another inflection point. You're changing from concave down to concave up. And F is a local min. So these are local mins, but B is also an absolute min. What are just inflection points? So just inflection points that I can see are C and F. That's where my concavity changes from concave up to concave down, and then concave down to concave up. Okay? I always look from left to right. So don't say that this changes from concave up to concave down. That's not true. It changes from concave down to concave up, because you're always looking. This is an x-axis, and this is where it's negative, and this is where it's positive. You're always looking from the left to the right. That's how we read math, basically. Okay? So concave down and then concave up. All right. So on the back, we're actually going to do some graphing, which I know sounds crazy. So all my papers that I wrote on. Okay. So number 3, it says find all critical points, inflection points, intervals of increasing, decreasing, da, 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 da. So here's what you're going to do first. Always, always, always. Just like before, you find your first derivative, just like you used to find your velocity, and then you solve for 0. Oops. And then you keep going, and you find your second derivative, and then you solve for 0, and then you get those. Okay, so now, what would you do if this was particles? If it was particles, you would draw your velocity number line and draw your acceleration number line. That's what you're going to do here too. Your velocity number line, I know at -1, at 0, and at +1, I have these critical values, critical points, and then I plug in on the, so I can do this 2 ways, guys. I can plug in 4 times, or I can realize something. So I'm going to plug in first. So I'm going to plug in like a -2. If I plug in a -2, this is negative, this is positive. Negative times a positive is negative. Okay, so I do that 4 times. Or here's the other trick. Are you ready? Let's talk about end behavior. End behavior. What does this look like? Generally, what does that look like? That's a positive x cubed. What's a positive x cubed looks like? It looks like that. Okay, this end behavior looks like that. It's a positive in front of x cubed. So, why would this help me here? Because if I just go like this, I can tell I start with negative and then positive and then negative and then positive. So this should have a negative and then positive and negative and then positive in my number line. Isn't that awesome? So you can do that, okay? Same thing over here. So I know I have a negative and then a positive 1 over root 3. I don't have to rationalize it, whatever, okay? I can plug in, so let's say I plug in 0. I plug in 0, and then I get a positive times a negative, which is negative. Or, instead of plugging in 3 separate numbers, like negative 5 and 0 and 5, I can instead realize that this function is a positive parabola that looks like that. So positive parabola, and if I go like this, I see, oh, this is above, below, above. Positive, negative, positive. So that is a shortcut. If you plug it in every time, it will take you longer. The shortcut is amazing. Okay, using end behavior, because you know what that looks like, and then you say, oh, okay, there's two points that it's going through. So then you just draw it through 2 places, and then you can see it's above, below, above. Positive, negative, positive. Okay? Okay, so how can that help us draw it? I'm going to ask you to do something like this. So I'm going to draw it first. Even though you saw it, you need to know how to draw it, okay? So here is what I care about. So at negative 1, at 0, and at 1, oops, let me look again. I have these critical values. I am going to go down, and then I'm going to go up, and then I'm going to go down, and then I'm going to go up, because it says negative, positive, negative, positive. So my graph of f has a negative, positive slope. Okay, now I'm going to deal with my concavity. So my concavity, if I have negative 1 over root 3, that's like around here. That's like my concavity right here. So these are my important points. So I'm going to draw my points. Those are my important points. I'm going to use another color, like, I don't know, a highlighter of pink. And then I'm going to draw my concavity. Ready? Until I get to here, I'm concave up. So concave up. There you go, concave up. Until I get to here, see the yellow, I'm concave down. So I have to go through my points, but I'm concave down. I kind of exaggerated over here. It's not so vertical, okay? And then the rest of it is concave up. So I have to touch my points. Concave up. This is what the original function looks like. Man, that totally makes sense though. The original function looks like this because this is an x to the 4th, and x to the 4th ends up, and it kind of looks like a W. Okay, so then I drew that as a general graph for it, and then you're listing out what are all your critical, well, I'll go like that. What are all your critical points? Well, you already found them, 0, negative 1, and 1. But then how did I get that y value? Oh, I plugged it back in. So I plug it back into here, and I get these y values. These are my critical points on f, okay? What are my inflection points? My inflection points are these. If I plug these back into the original, I get y values. These are my my inflection points, okay, that come from these x values. I plug it back in to get the y values. I'm increasing, I can see it right here, I'm increasing from negative 1 to 0 and from 1 to infinity. I'm decreasing from negative infinity, to 1, negative 1, and then 0 to 1. So those are where I'm positive slopes, and then I'm negative slopes for my first derivative. Okay, so first derivative, and then that's my positive and negative slopes for my original. Okay, concave up, where am I concave up? I can tell here in my f prime graph. I'm concave up from negative infinity all the way to this value. And then I'm concave up from this value all the way to positive infinity. When am I concave down? I'm concave down right between here. It says negative for f double prime, so that's where I'm concave down. Okay, so once you do all of this stuff, this is easy to see. In the next problem, we're going to do an even better graph using those points and using what we know here. Okay, so using all this stuff, using those points with the y values and everything. We're going to do everything for this problem. So this says, find all absolute and local, minimum and max values. So we're going to actually graph it, because you guys have to know how to graph it as well, okay? On the homework, if it doesn't ask you to graph it, you don't have to. But I need you to be able to graph it for like the mini quiz, the quiz, all that stuff. Okay, so what are you going to do first? Same thing, find the first derivative, and then solve for 0. And then if you want, you can go ahead and start your little number line. So at right here at -1 and 2. Okay, at -1 and 2. There's extra numbers, you'll see why. And then you have your, I'll go like this. Oh, wait. Oh, that's fine. Okay. So I have these, that's fine. So I just have these. I don't really need my second derivative, you'll see why. Okay. So it's nice to have, but I don't really need it right now. So I have these two, and then how come I wrote -2 and 3? Because those are endpoints. So I need to make sure I end it at -2 and 3. Okay, so I start here, I end here, and then I have these two x values there. Okay. So here's what I know. Because this is a, remember we did this is a positive parabola, and then I draw my little, there's two values here, so when I draw, I would have positive, negative, positive. That's why it's positive, negative, positive. I can also plug in a number between, so like -1.5, I can plug it in, but it's kind of annoying. A 0 and like a 2.5. If I want, I can plug it in to get my positive, negative, positive. I know this has to be a local max because it's going from positive to negative slope. This is a local min because it's going down and then back up. Okay, local max, local min, and then I have to check these. So how did I get these y values? Well, these y values you plug into here. These x's I plug into here to get those y values. Okay, what about these two right here? So I plugged in my endpoints, right? So what about these two? Well, the -1 comes from here. I plug it into here and I get a y value. Then 2 comes from here. I plug it in and I get a y value. Okay, so I have these. And then I'm going to sketch it. I know you can see through my paper, but I'm going to sketch it. It goes up, down, up. And then these are my points. So it's going to look something like that. How do I know what the concavity is? Because I know that this is smooth and this is smooth. I know that it's smooth, so it's going to look something like that. So if you want, you can find the second derivative and then you'll see that this is true, but it's definitely going to be all nice and smooth that way. Okay, so using this, I go up, down, and then up. So up, down, and then up. So I can see my lowest x value, sorry, my lowest y value is right here. My biggest x value is actually right here. Oh, y value, sorry. My biggest y value is actually right here. So this is a negative, negative, negative. This is a positive. So actually, this is my local max and my absolute max. And then this is my lowest y value. So this is my local min. And also, I can tell, this is my absolute as well. So I list those. And I should be able to draw that. And if I asked you to draw it really nicely on an XY plane, you should be able to draw it, especially with these 4 points. So you would graph your 4 points, and then you go ahead and, you know, fill in your concavity because you would get the second derivative, and then you would see where that point was. So right now I don't know where that point is, but I can do 12x minus 6. I think I get x equals like 1/2. So really this is x equals 1/2. And then when I find my concavity, I would see, oh, this is a negative, and then it's a positive concavity. All right, so I know that was a lot of explaining, but I want it to be super clear because this concept is really important, okay? Good luck, guys.